Hello and welcome to this video. In this video we're going to go through the topic of diffraction. Now I've mentioned the word diffraction a lot throughout this course actually, but we've never actually explained fully what's actually happening with diffraction. So you may have heard me talk about it when we looked at interference, because that's quite closely related with this, but you also may have heard me talking about it back in quantum physics when we were talking about electron diffraction. So hopefully now I'm going to use these videos as an opportunity to explain to you what diffraction is, and this is something that you will be examined on, so make sure you're paying attention. Okay, so the idea of diffraction is we generally use it as this is evidence that light behaves as a wave. So this is evidence of the wave nature of things. Okay, so it's evidence for the wave model. We know that from particle wave duality or wave particle duality, things can be waves, things can be particles, things can be both, and anything in between. So this diffraction is the evidence of when they behave as waves. So the reason this is evidence is because we see interference. Okay, now interference being constructive and destructive interference, meaning we can make bigger waves and we can cancel out waves, and we shouldn't be able to do that if we were looking at the particle model, because we can't have two particles that come together and then make nothing unless they're antiparticles. Okay, but we don't have particles. Let's say we're just firing pure electrons at a screen, we'll still see an interference pattern. So the general setup for diffraction, we can look at single slit diffraction, which is what we're going to look at to begin with, which is where we're going to fire light. So let's say that this is the slit. We're going to fire light through a small slit when we only have one slit, and then some distance away we're going to have a screen. Okay, so this is just a screen. This here is the single slit. I'm going to put these waves of light in red so that we can see that it's usually going to be a monochromatic source. When you do the practical for diffraction, you will do it with a laser, so you will need a monochromatic source. And we're taking a top-down view of this. Okay, so we're going to say that we're going to look from the top, and so we're going to draw what we call wavefronts. Okay, so wavefronts are our way of drawing light so that every time it reaches a peak, so every time it comes up, we draw a wavefront. It will then go down to the minimum and then come back up. We draw a wavefront there. Okay, so the distance between these two is your wavelength. Now, what happens when it passes through this small slit is it basically gets squeezed through, and so when it gets squeezed through, we have this kind of curving effect where it is going to spread out. And when it spreads out, it's going to reach all the way across this screen. And we're going to see on the screen, we would expect, if we can accept that this is going to spread out, we would expect to see just a whole like faint line of red light. But what we actually see on the screen, I'm going to draw over here first, and then I'll see how that changes. So what we actually see in the very middle of it, we see quite a bright red strong peak in the center. Either side of that, we'll see some sort of black patch, and then we'll see a slightly smaller peak either side. Then we'll see a smaller peak either side of that, and we'll see a smaller peak either side of that, and this will keep going. So this is what we'll generally see as a diffraction pattern. And this is what we call diffraction pattern. Okay, where all of these are called fringes. Okay, or we can also refer to them as maxima. Okay, so they're maxima because this is where light has its maximum intensity. So that refers to all of these red spots. And therefore all the spaces between these red spots are called minima. Okay, so these are all minima. What this means is if we're getting some diffraction pattern here, and we're seeing some blank spots where we're getting no light, it means that we have interference. That's the whole idea of diffraction, is that light is going to constructively interfere. Light constructively interferes to form fringes or maxima, and then it's going to destructively interfere. Destructive interference is going to cause these minima. Causes the minima. Okay. Now, what should be racing through your mind currently are a lot of questions about this, because when we first observed this phenomenon, it didn't make any sense. Okay, why is it possible that we can have, especially with a single slit, where we have all of the same light traveling through, how can one light source cancel out with itself? Surely it should always be in phase with each other, which is why this is very strange with a single slit. What we're going to look at first then is looking at the double slit, because we can use it to make a little bit more sense, and then we'll come back to this single slit and explain it in more detail using Huygens principle. So let's take a look at the double slit diffraction and how that's going to change. Okay, so now let's have a look at double slit. And so what happens in double slit is very similar. We're going to have two slits in this case. So this is the slits. Some distance away, we're going to get the screen. We're still going to have that light source. So we're still going to have these wavefronts that are passing through, where this distance between them is the wavelength. But when they pass through this, they're going to spread out like this, and so on. And then we'll have others of them that are going to spread out like this. And so on. Now, this should make more sense as to why we see this interference pattern. I could point out that there are places where we have crosses, where we have this crossing over of all of these light. Obviously, I've only drawn these up to here. When we go out, and this is not very accurate, we'd also have one there as well, and one there. If we were to go out to have more detail, you'll find you'll also get one down here, you'll also get one over here and over here, and so on, right? So you're going to get a lot of interference, and so what we see on the screen is going to be slightly different, because each of these, so each slit behaves as a secondary source for waves. Okay, so even though we only have one source, which is the laser is still providing all of this light. When it passes through two slits, both of these slits now act as if they are the new emitters of light. Okay, this is a consequence of Huygens' principle that we're going to look at in just a bit. But what we see is going to be slightly different to what we saw in the single slit diffraction. We will still see a large original, so we'll still have a central maxima, but the central maxima is now going to be split into a few more. So instead of having just a large dot, so what we should see is a large circle, we actually see smaller lines that do this kind of effect, and we don't have that kind of circle. Then we get a bit of a gap, and then we have lines over here that make a smaller dot, and also lines over here that make a smaller dot, and then we'll get obviously smaller as we go out. Okay, and so we are still going to get this kind of interference pattern, but now we've split all of these maxima into these shorter fringes. Okay, that's a consequence of having two slits, because when we have the two slits, it means that we're going to get even more interference in the middle of a certain fringe or a certain maxima, that's going to cause it to split, and we're still going to have small gaps in between each of these things. Okay, so what is happening here is a little bit easier to explain than in the single slit. If we were to treat each of these, I'm just going to get rid of this mess for a second, and I'm going to put on here and say that I'll go back to red just to stay consistent. Dead in the center here, we're going to have that big maxima. I'm not going to draw it like this, but this is how it would actually appear. We have the central maxima, and then we have maybe the subsidiary maximas certain distances away. Okay. Now, to get from the first, so let's assume what we can call these things is they all have an order. So the central one is n equals 0, this is n equals 1, this is n equals 2, this is n equals 3, but you would expect this to be negative, but it's still the first maxima, second maxima, the third maxima, because it doesn't matter what direction you go in, the maximas are identical. Let's say we wanted to get to this first maxima. The light from this, if we were to draw it as a ray rather than curved lines, has to travel this distance, which is equal to the slit distance, the slit screen spacing, which we're going to refer to as uppercase D. Okay, has to travel that distance. Now, the light from here has to travel across here, which is a slightly longer distance. Okay, so there's a small difference here, which means that we're causing what's called a path difference. Okay, so a path difference is just a difference in the length of the path that light is taking. Or let's generalize it to the wave. Okay, what the path difference is going to do is cause some sort of phase difference, because if we have something that's traveling an extra distance equal to half a wavelength, it means that when we start, this one original wavelength that's traveled here, the new wavelength is now starting half a wavelength behind, and so it's going to start here and completely destructively interfere with the original wave. Okay, so we can use this idea of path difference to now have another definition for what phase difference is. So now we can say that phase difference, where before we said if things are in phase it had to be 0, 2 pi, 4 pi, we can now say for it to be in phase it has to be n, or let's just call it wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, or we could generally just call it, or 0 even. And in general, we can just call this n lambda. Okay, so it has to be a whole integer number of wavelengths. Now I'm going to underline this because this is going to be an important thing we have to refer back to in a second. So for things to be in phase, they have to be a whole, the path difference needs to be a whole wavelength across. Okay, therefore in antiphase, for antiphase they need to be half a wavelength across. So that would be, in general, we'd call it n plus a half multiplied by the wavelength. Okay, so where n is a whole number, so n could be 0, and then the difference would be a half wavelength. N could be 1, and then it'd be 1.5 wavelengths, and so on. Okay. So here's the thing. If this path difference from the two slits is equal to a whole number of wavelengths, then by the time they reach this point where this maxima is formed, they will be in phase. Okay, so we have to now say that there is some sort of slit or path difference that's causing this to reach here, where both of the waves will be in phase with each other, they will constructively interfere, and they will form that fringe. If we were to go a little bit further along, then they both have to travel a slightly longer distance. And if that distance is not equal to a whole number of wavelengths, then it undergoes destructive interference because they're in antiphase. As long as it's exactly a half, there'd be kind of a small decrease in intensity. We'll have a look at the intensity profiles of these things in a bit. We'd have a phase difference, a path difference that's going to cause a phase difference of half pi exactly in the middle of these two things, which is where we reach the minimum amount of light that we can get there. Then we'd slowly go up. We'd have a whole number of wavelengths here. We'd have a whole number of wavelengths here, and so on. Okay, so all of these fringes and minima are caused because of the path difference between these two light rays. Okay, now this is double slit. There's only one extra type of slit to look at, and that is a diffraction grating. So now let's look at this idea of diffraction gratings. Now diffraction gratings so we have the exact same setup. We have a slit, but instead of having one or two slits, we have a bunch of slits. So we have a whole, like a very high number of slits. And what that means is that we're going to have even more interference because we have more things that all act as secondary sources for the wave. So we're going to see a different type of interference pattern on this screen, but we'll still have the same setup. We still have light coming in with these wavefronts. They'll still undergo these circular type of diffraction, and the pattern that we see is going to be much more spread out from what we originally had. Okay, so what we originally had, so this is the single slit. So let me just iterate. This is what it looks like when it's single slit. We had the central maxima, and then we had smaller maxima either side that then generally decreased either side of this. Now the diffraction grating is going to have something that looks more like a line here, which will be its biggest maxima. Then its second maxima will be out here. Then its third maxima might be over here and off the screen. So we have basically a much larger, what we would call fringe spacing. Okay. So in general, we need to be able to compare between what would happen if we looked at the intensity profiles and the observations from single slit, double slit, and diffraction gratings. So let's take a look at that. So this is kind of a summary of these things. So let me go back to white pen. So this is a summary of the observations of the things that we would see with this. So let's first look at an intensity profile. Okay, so the intensity profile, I'm going to color code these because I'm going to hopefully be able to do all of these on the same profile. I'm not too sure if I'm actually going to be able to fit them all in, but hopefully I should. So let's say that white is going to be the single slit. That's what this is going to look like. I'm then going to have red as a double slit, but we'll do that in a second. So a single slit, what we have here is basically the y-axis is intensity, the x-axis is the displacement. This O here is where we see the original maxima on the screen. Okay, so either side of this is going to be maxima. Now the central maxima has the highest intensity, so it looks like this, then decreases, and then at some distance away we'd get a second maxima, that would decrease, and then we'd get a third, and then so on, and it will be symmetrical on this side. My drawing is probably not going to end up symmetrical, but it should. Okay, so yeah, like I predicted, not exactly symmetrical, but you get the idea. It should be a symmetrical line between the two of them. Now the double slit is going to be, so the double slit is going to have smaller interference patterns in between these. So we're still going to have a central maxima that will reach the same amount, but that central maxima is going to be split into smaller fringe patterns. Okay, so that is then going to look more like this, so on. It will reach some sort of minimum, and then the next ones are also going to be split up. Obviously my drawing is not the most accurate, but you get the general idea of what's going on, in that these things are going to have be split up. I'm probably not going to be able to draw a diffraction grating one over this, and that's because this whole envelope is going to become much larger. Okay, so let me draw a smaller sketch for what the diffraction grating one would look like. If we know that the spacing between these maxima is going to increase, then our graph of intensity against displacement is going to be much thicker. Okay, so it's going to be much more like this on either side, because we've spread out that intensity across a much larger distance. Okay, so hopefully this all makes sense. This isn't all of diffraction that you have to know just yet. This is kind of just the introduction to the phenomenon and talking about the different types of slits that we can have. We're going to go into a little bit more detail and look at some calculations in the next video, so stay tuned for that. And